I accidentally left my mic in my previous classroom. I went down, I figured out it wasn't in my office, so it must be in the previous classroom. So I went down there to get it, and then I had to wait for the other instructor to finish praying. She prays a long time. Like, it just kept going and going and going. So, anyway, don't worry. I know I'm starting class late, so I'll end class early, naturally. I know you guys need to vote, right? Yeah, I know. So, let me turn the lights on here. There we go. Right. So I will begin with a word of prayer. Let's see here. So I'll begin. Heavenly Father, we thank you for this day. I thank you for the students. Just ask you to bless our work today, Lord, and just help the students to vote if their vote is a good vote. Amen. Let's hear. Whatever that means. So guys, do you have any questions about, well, let's say physics. It seems like I should probably limit the discussion to physics. It's usually a good idea. Here's the attendance sheet, which is of course optional today, so I don't know why I'm even bothering, but I mean, yeah, it is. Pretty much. Do you get extra points?
Yeah, for being here.
I mean, I think you have the reward of my teaching. No? Hey, that hurts. All right, so any questions? We are in the middle of the rotational physics, yeah? Any particular problem you'd like to see me work? I'm taking requests. Preferably the ones I've recommended, yeah. Which one?
I think, let me look, but I think I have.
Will the syllabus be updated after Thanksgiving break?
Syllabus be what?
Updated after Thanksgiving break.
Oh.
It says to be announced.
That's right. Well, that's one of the exciting things that happens on test 2 is I will give you a choice of topics after test 2. And you get to choose. And whatever people choose the most of will do. If everyone says, I don't want to do anything, then I'll do something you all won't like. Yes?
With that, will those mysterious topics be on the final?
Yes, they would.
Okay.
But I think the final is primarily about the material in test 1 and test 2. So probably something like, I don't know, 45% test 1, 45% test 2, 10% stuff after test 2, something like that, most likely. Yes, sir? Number 25 on page 223. Sounds like a winner. Oh, yes, thank you. Good question. So here we have the axle of a wheel shown in figure 8.42. We're supposed to assume that the friction torque of, there's a frictional torque frictional torque of, let's see here, what was it? 0.6 Newton meters opposes motion.
What question is
This is number 25 on page 223. So frictional torque, and then we have this picture. See if I can recreate it. There's a circle, and then a larger circle. We're told that this is 12 centimeters. We're told that this is 24 centimeters. And then we're given three forces which are applied, and then what are we supposed to find? The net torque about the wheel of the axle, right? So this question is about, there you go. is about calculating net torque. So I haven't pictured the forces yet. What are the forces? 18 newtons, like this. We got that force there. Let's call that F1. We have 28 newtons right here. I'll call that F2. You know, F1 and F2 are not given in the problem. I'm making up these labels, guys. And then there's a third force, which is applied to the inner wheel at 135 degrees. And that third force is 35 newtons. I'll use green for that one. And that's F3, let's say. Now there's a third force, there's a third torque, which is the frictional torque, right? What direction does frictional torque get applied to? The opposite, the direction of what? Motion or potential motion, right? Whether or not this actually turns depends on the question of whether or not the frictional torque is outdone by the forces, the torque that the forces pictured actually apply. Whoa. Not much frictional torque in that door. Let's see here. So how do we figure out torque from force? What's the formula? R cross F, right? But here, a little bit easier. So let's use the right-hand rule. I'm going to define the axis coming out at you as the positive direction, which means that counterclockwise, we're going to say this is positive direction. All right? And so we can talk about the torque from 1. Let's do that to start with. What's the torque from force 1? This force is applied this way, right? Yeah, it's creating a negative torque, so minus what? Yeah. Well, it's R, let's say it's R1, F1, sine theta 1. Now that sophistication is not really necessary here, because if you look at R1, which is this, see, that's R1. And if you look at F1, which is this, the angle between them is 90 degrees, right? In other words, force 1 is producing the most torque it can possibly produce because it's exactly perpendicular to the radial direction. And like you guys told me, there's a minus there, so. And what's R1? It's 0.24 meters times 18 newtons with a minus there. That gives me the torque from force 1. How about the second torque, torque 2? Actually, all of these forces are applied perpendicular to the radius, so we're just going to do the force times the radius every time, okay? I won't even write the sine theta again, because theta is 90 degrees between the radial arm and the force applied in each case, right? Like, see that? This angle, 90 degrees, right? And same thing over here. This angle, 90 degrees, right? Okay, so how about torque 2? Is that creating a positive torque or a negative torque? If I push it like that, it's creating this kind of motion, right? That's a positive torque. So we do 0.24 times 28 newtons, whatever that works out to. And what's torque 3? So this time, is that positive or negative? Negative, right? Because it's trying to make it twist that way. So minus 0.12 this time, because it's at the inner radius, times 35 newtons. All right. Now that's everything except for friction, right? Still got to think about friction. I don't know which way friction goes yet until I do some number crunching here. 0.24 times 18 as the negative one. Let's see here. So the first one's 4.32, rather minus 4.32 Newton meters. The second one, yeah, 6.72 Newton meters. The third one, yeah, minus 4.2. So what happens if you add these up here? Looks like we have torque 1 plus torque 2 plus torque 3 equals to minus 1.8 Newton meters, right? So then now we understand what direction the frictional torque goes. What direction does the frictional torque go? Yeah, it goes opposite the net torque, right? So this implies that the frictional torque, and we're given the value of it, right, is equal to 0.6 Newton meters. What was that beep? What's that? Oh, just that. Okay. I'm always worried about my stupid power cord undoing itself somehow these days. It makes a kind of similar beep. So. Very professional. Let's see here. So, do you guys understand? That has to go opposite the net torque otherwise. Does that make sense? So then what's the net, then what is then, in fact, what's the total torque then? Including friction. Minus 1.2 Newton meters, yeah. So I could include it in the picture now, right? The frictional torque goes like this, in fact. It's a clockwise. Wait a minute. I'm an idiot. Other way, right? It actually produces the counterclockwise. Wait a minute. Yeah, counterclockwise twisting motion, because we said it was 0.6 Newton meters. Now, I don't have the answers in the back of the book, did I? Am I good? All right. That's good. Yes, sir.
So even though the problem in the book shows the angle for F3 to be 135 degrees,
Ah.
it doesn't really play a role.
Well, what's that 135 degrees? Oh, you wanted to use sine on 135? I mean, you feel like they give you an angle, we should use it? Yeah. Well, that angle, what that angle did for me was it told me that, and you can see it from their picture too, but that 135 degrees was this here, right? And so that just gave me the perspective that, you know, this line, which I guess is y equals minus x, has the green line as a perpendicular bisector, which shows you that the radius arm here, which is this one, that would be R3, right? That vector R3 is perpendicular to the green, so that's why I just multiplied them. Well, I'd have to draw a different picture. I mean, you could have something along the lines of, here's one where it would be different. If I had this wheel, right, and I somehow apply a torque apply a force rather, like this, right? And suppose, you know, that angle, let's see here. I could tell you that this is 30 degrees, and I could tell you that this force is, you know, horizontal. And then I could ask what's the, you know, if this force is equal to, let's say, 100 newtons, and say that the radius is 2 meters, I could ask what's the torque developed from such a force being applied in such a geometry. That would be an interesting question related to the one you're asking. So what would you do? So I'm supposing the pivot point is the middle of the wheel, right? So the first thing I do is I think about what's the radial arm, like where, what's the vector which connects the pivot point to where the force is applied, which would be this guy, right? So I have to think about it like this. I've got my radius, my radial arm rather, I've got my force applied, right? This angle's theta. And I know that the torque is a vector, in fact, and it's equal to r cross f. We don't really need to do all that, but the magnitude of r cross f, right, is rf sine theta, right? So the cross product of two vectors is largest when they're exactly perpendicular, and it's 0 if they're parallel. That's why cross product's a good formula for torque. But anyway, I guess my question is, what's theta in this situation? Can you see geometrically what theta is? So one way to see it would be to think about taking this vector r and just parallel translating it up here, like that. Okay, like that. And if you can imagine doing that, you can see that this 30 degrees is also this 30 degrees. So in this case, the angle given is actually the angle that you want. But you should think through it, right? An evil physics professor could do something nefarious like, I don't know, instead of telling you 30 degrees, go and say, hey, 60 degrees is up here, what do you know? Right? And if you weren't thinking about it, if you were just blindly supposing that the angle that you're given is necessarily the angle you plug into the formula, well then you'd be in trouble, right? So we should think through it. It's the angle between the force applied and the radial arm. So anyway, getting to it, the torque, the magnitude at least, would be F r sine of theta, which in this case would be 100 newtons times 2 meters times the sine of 30 degrees, which I happen to know is a half. So apparently 100 newton meters. Next question, what's the angular acceleration for such a wheel? If you applied that force, what would the angular acceleration be at that moment? If you apply the force like that. Now that question we can't answer until more information is given, right? So you guys tell me, how much mass should the wheel have? Yeah, suppose that the mass of the wheel is 10 kilograms, right? And we'll assume that the wheel looks something like this. This is just a boring, essentially a flat, it's a cylinder, right? Then the moment of inertia, in this case, this geometry, is 1/2 mr squared. So the moment of inertia for such a wheel is 1/2 times 10 kilograms. What was my radius? 2 meters squared. So I get what? 40 divided by 20 kilogram meters squared would be my moment of inertia. So what would the angular acceleration be in this context? Remember, torque is equal to moment of inertia times the angular acceleration. So I've just calculated that the torque is 100 newton meters, right? I just calculated that the moment of inertia is 20 kilogram meters per second squared, so my alpha would be, 5? What'd I do? What's 5? What did I do? Oh, you're telling me it's 5? Oh, okay, good. I just, you guys are doing the math in your head. Oh, good. I like it. I got to write it on the board. Let's see here, tau over I, which you guys have sophisticatedly done. So apparently you can calculate that 100 divided by 20 is 5. And I view that as a good sign. Like, that gives me hope. I mean, it's good. It's really good. 5 what? I wasn't trying to be mean.
Okay.
Hey, listen, like I just saw a physics question. It was given to physics 232 here. All right. Let me try to restate it in terms you'll already understand. My car has a gas tank that has a 20-gallon capacity. I go to a gas station, and they fill my gas at twice the normal rate. What can you say about the capacity of my gas tank? Yes, it's still 20 gallons. What the students answered on this test, 80% of them, is that if you fill the gas tank at double the rate, the size of the gas tank doubles. That's how lost they are in terms of understanding what capacitance means. It's not good. It's not good. They need to come back to this class? Maybe that's the problem. They never had this class. Let's see here. So that would be 5 radians per second squared. So this is the angular acceleration. If you could somehow continually apply that force over the period of its angular motion, you'd have a constant acceleration of 5 radians per second squared. And then you could do other questions with that. Questions? Yeah.
I think this is probably a stupid question, but how do we know that it's radians per second squared?
Well, that's the units of angular acceleration. So we have theta has radians. Omega has radians per second. And the units for alpha are radians per second squared. More specifically here, if you work through it, a newton is a kilogram meter per second squared. So when I take a newton times a meter, I get a kilogram meter squared per second squared. So the newtons the kilograms and the meters squareds cancel, and it just leaves you with a division by second squared. The understanding that you have to put radians there is that we're working in radians, so that's the custom, is to write radians. But some people would say the real units are 1/second squared, but I say those people are stupid. So, well, they're not stupid, but they're just wrong. Radians per second squared, yes. Degrees per second squared would mean something else, yeah. Okay, next question. Yeah. Uh-oh. Seems like a trap. Ah! You're making me work. It's fine. I'm just kidding. This is a good problem. Let's work it out. You got to understand, my blood sugar is just a little bit low because I thought class would be canceled, and I didn't even bring my real shirt today. I thought this was going to be a freebie. Little did I know. I thought they were going to zig, and they zagged. What can I tell you? Let's see, page 224. Did you say 46? An even number. Oh, okay. I must really like this problem. Two blocks are connected by a light string passing over a pulley of radius 0.15 meters, and moment of inertia I. So this problem's got lots of goodness in it. Let's see here. So we've got a pulley up here, and we've got two masses. And what else did we learn? MA of 8 kilograms. And over here, MB of 10 kilograms. What else do I know? This is 32 degrees. And this is 61 degrees. Which means that that's not a right angle, right? What's 32 plus 61? (93). So that, I'm assuming that this triangle is in a Euclidean geometry, so that the sum of the angles is 180. 93, yeah? You guys know if you have a triangle in a curved space, it can have other things, right? By the way, if you look at the triangle in a sphere like this, that's got 3 right angles. So the angles inside that triangle, that curved triangle, are 270 degrees. In fact, if you measure the angle at the interior of a triangle and you get more than 180 degrees, congratulations, you just figured out you're inside a curved space. That's why it's 270, is because the sphere is curved. I think I may be digressing slightly from the problem. Okay, so 93 degrees. Oh, really? Oh, I can't do math. I was assuming it has slight curvature. My apologies. So 87 degrees? Cool. So it's almost right. I mean, I was almost right. But it's almost right. All right, I'll shut up. Radius of 0.15 meters, the pulley, right? And what else do we know? Oh, we're told that the blocks move toward the right with an acceleration of 1 meters per second squared along their frictionless inclines. Frictionless. The acceleration is 1.00 meters per second squared to the right. Media would not be happy. Let's see here. So, like that. What else do we know? We're supposed to draw free body diagrams for each of the 2 blocks and also the pulley. We're supposed to figure out the tension from A, the tension from B, and also the net torque acting on the pulley, and determine its moment of inertia. Oh, okay, I like this problem. I guess that's why I recommended it. Let's work it out then. All right, so of course we have what? We have the normal force on B. And what else do we have going on here? Yeah, we've got, yeah, exactly. We've got different parts of, I'm trying to think here.
The X and Y direction thing. Like force of the X direction.
Well, I was going to try to give the part of gravity which is like this, right? And then there's another part which is like this. So that would be MBG sine of 61, I believe. Whereas this one is MBG cosine of 61 for that piece. And then, of course, there's the tension force, which I'll draw in green, like this, right? I'm glad they didn't put friction in this problem. That would be a real drag. Let's see here. Friction. Sorry, that's horrible. The force of tension from, let me just call it FB. All right? FB. See, FB is also up here pulling on the wheel. All right? On the other side of things, we've got, of course, the normal force for A. We've got our handy-dandy mg cosine of 32 over here. And we have over here and that's a MB. Oh, good grief, MB, listen to me. MA, right? MA G sine of 32. Let's see here, what else? Oh, of course, the tension force, like this, FA, and that, of course, is pulling back this way, like that. Are there any other forces on the blocks? I think not. I think it's the tension, the gravity, and the normal force, right? And then on the pulley, you just have the two tensions pulling on it, right? And I need to blow that picture up because the angles there might be a little bit subtle. All right, maybe. I gotta think about that. Well, before I do that, let's just go ahead and write Newton's second law on the masses. We can do that, right? So what's here? We've got what? M. Let's write down here. MA. Oh, this one. MAA is equal to what? It's equal to FA minus MAG sine 32. I believe that's it in terms of the parallel direction to the plane, right? The normal force and the mg cosine 32, those got to cancel out. And then on the other side, Newton's second law for MB, MBA, over there, you got yourself an MB sine 61, because that's in the direction of the acceleration, so it gets a plus, and minus FB. All right, I've avoided it as long as I can. Now we got to think about the torques on the pulley. So, what's that? I'm trying to think. Are those, what's the deal? It's so close to right. Maybe it doesn't, I don't know. I'm trying to figure out if those forces are applied at some angle to the radial arm up there or not. If they're not, then it's relatively simple. I'm probably supposed to think that they're not. Stupid picture of my boxes. Well, I don't know. It should be. I'm just probably I'm probably making things more complicated than they need to be. I'll do that sometimes, you know, guys. Is it possible to pull a string along a pulley and not pull tangent to the pulley, or do we have to pull tangent to the pulley? Do you know what I'm saying? If I have a wheel like this, right, and I wrap a string around it, and then I'm over here pulling on it, right? Could I somehow, however I pull on that string, right? Does it have to be, yeah? Depends on the what? Orientation of the pulley. But I think that would I don't know, I think maybe it would just change the contact point of the string on the pulley.
The box or the pulley?
Like, if you think about the wheel, right? That's what I think. I think since it's around a circle, it's always going to be tangent. But I'm worried that it wouldn't be, and so, but I think I'm wrong to worry. So, long story short, if we can chase down our geometric demons here, I think that really, oh, well, so this is a picture, roughly speaking, of FB, and, right? I mean, is my picture wrong is my question. Does that have to be? Oh, it really depends on how the string is. I got to look at my diagram. It depends on how the string is attached to this. It's supposed to be parallel to the plane in the diagram, all right? So like, my original picture is better. This one seemed, I mean, well, okay, I guess it's still. Okay, yeah, right. Let me see if I can recreate the magic of the book diagram. That it's easier to see in that one. My diagram is somehow not helpful. I was trying to make it blow it up so it would be easier to see, and I think I somehow managed to make it worse. Try again. All right, here's my attempt. So if you look at this silly thing, the FB is like this, and if you look at the stupid FA is like that. The point is those are not applied radially to the center of the pulley, right? They are at an angle, which we have to account for. If you look at it, you can see it more clearly if I actually just draw. The picture is such that you can see that it's like this, and that one's like this. So this is the radial arm, and then FB is parallel to the, like that. So I'm trying to see what the angle is. What's this angle here? I need to figure out that angle. I think it's 61 degrees because it's an alternate interior angle. If I look at the one up at the pulley and the one down here, and then I look at this, and then I look at that, then this angle and that angle are the same. So I believe by alternate interior angles that's 61 degrees. And the other one would be 32. And as such, the torque, right, would be equal to, what was that radius? 0. R times F, R times F, A times the sine of 32 degrees, and then RFB, and I haven't thought through the sign, like SIGN here yet. You guys tell me about the sign. If we're going to say that positive torque should be what? It should be, we're trying to match positive torque with positive acceleration. So if it's moving to the right, let's say that's positive direction. So moving to the right would mean that clockwise rotation is positive in this problem, right? Positive to match A being greater than 0, okay? If we're saying positive direction is rightward, then that corresponds to the, that's clockwise, right? Yeah. So which one of these torques is clockwise, which one of these the B one is clockwise, right? So we do plus RFB sine 61, and we do minus RFA sine 61. And what's this all equal to? That's the net torque. What's it equal to? this should be equal to the moment of inertia, which we don't know. That's the whole question, is to find the moment of inertia times alpha. What's alpha? We're assuming that the string is going over the pulley without slipping, right? So there's a relation between A and alpha is what? Alpha is A over R. So this is actually A over R. And then at this point we're done. Because what we have is 1, 2, 3 equations in 3 unknowns, because we know R and we know A, right? So we can solve these to figure out what, in fact, you don't even need to do algebra. You could actually just manhandle the first 2 equations to figure out what FA is and FB is, right? They've set this problem up so you don't even need to solve 3 equations and 3 unknowns. The book has been pretty nice here, actually, in terms of setup. It doesn't actually require the genuine 3 equations, 3 unknowns algebra. Because if you look at this, like either one of these, we can calculate FA. What's FA? It's ma plus mag sine 32. Whatever that is. I don't know. I mean, we know it's 8 kilograms. 8 kilograms times, what was it, 1 meter per second, plus 8 kilograms times 9.8 meters per second squared times the sine of 32 degrees, whatever that works out to. That's my FA. My FB. What we got? We got MB G sine 61 minus MBA, which would be, 10 kilograms, I'll factor that out, times 9.8 meters per second squared times the sine of 61 degrees minus, minus 1 meters per second squared. I just decided to factor MB out. And that will calculate MB, right? I mean FB. So can you guys tell me what you got for those? So what, anybody get FA? Negative for FA? 45.9? And how about FB? 75.7? 75.7 newtons, okay, I'll take it. And so then to calculate the moment of inertia, we just go put those over in here. I solved the red circled equation for I, yeah? And so you can just plug in FB and FA into there. And we know what the radius is, right? So we got minus 45.9 newtons times the sine of 32 degrees plus 75.7 newtons times the sine of 61 degrees, all divided by 1.0, well, division by 1.0 meters per second squared. That's not too hard. And all that's supposed to be multiplied by the radius squared, which is 0.15 meters squared. So my moment of inertia, I'll calculate it here in a minute. Uno momento. Let's see here. 45.9 sine of 32. I'm supposed to put a minus on that. Plus 75.7. So sine of 61. Ooh. Well, that's good. It's positive. It'd be kind of concerning if the moment of inertia was negative. Like, that wouldn't be good. Moments of inertia are supposed to be positive. Just saying. I calculate 0.942. And what are the units? Well, 0.9424 for what it's worth. And the units on that, of course, would be kilogram meters squared, given my setup. And that should be the moments of, the units for moments of inertia are mass times length squared. That's a nice problem. Actually, it's kind of disappointing. They gave you too much information. You didn't really have to do the genuine 3 equations and 3 unknowns. It's kind of disappointing for me, personally, from a mathematical perspective. They could give you less and still have you work out the physics here, but they're actually kind of being nice to you, telling you as much as they did. Might not seem that way, but yeah. Next question. Is that good? Hey, okay, good. The larger point is that when a pulley has mass, we need to look at the sum of the torques on the pulley and say that it's the moment of inertia to the pulley times alpha. That's how that enters in. So there's a rotational Newton's second law for a pulley with mass, which we have to account for. That's kind of the new wrinkle. Yeah. You guys get questions? Yep. Aha.
Radians to revolutions, which is like 1 revolution is 2 pi radians.
Uh-huh.
That in your calculator exactly.
Ah. See, so the question is how to convert, is it radians to revolutions or vice versa? Great question. So the basic idea is a revolution is when I go all the way around, right? That would be 1 revolution. So the question is, 1 revolution corresponds to how many radians? So, how many radians are there in a circle? 2 pi, exactly, 2 pi radians. And so that's basically it. So if I want to convert radians to revolutions, so if I got like 50 radians, what I do is I take that and I multiply it by 1. But the one I'm interested in is 1 revolution divided by 2 pi radians. So then the radians will cancel, and that's how I convert. I just multiply, well, long story short, I divide by 2 pi. That gives me the number of revolutions.
So you don't actually have to put radians right.
Oh, no. You don't want to, we write the units on the paper and let the calculator deal with pure numbers. I suppose you could imagine a calculator which handled unit calculations, like you actually put in not just 10, but 10 meters, and you actually put in the units along with the numbers, but I've never worked with such a calculator. Perhaps one exists.
That makes sense. I just wasn't sure
I think
if radians were canceling out.
Wolfram Alpha would probably do that sort of thing, but yeah. So this is just an abbreviation too, right? These cancel, and we're left with 7.958 revolutions. Yeah. And this is, generally, advice on how do we convert from one system of things to another, right? Like if I had 50 miles per hour, what do I do? First of all, I imagine that as miles over hour, right? And then I multiply by things that are equal to 1. So, for example, I happen to know that 1,609 meters is equal to 1 mile. So multiplying by 1,609 meters divided by 1 mile is just multiplying by 1. And I happen to also know that there are 3,600 seconds in 1 hour. So I could multiply by this, but that would be stupid. See, because then they don't cancel, right? So that's not the right one. It's not the one you're looking for. Instead, we should do 1 hour divided by 3,600 seconds, and then we will be good to go. We'll figure out what 50 miles per hour is in terms of meters per second. So let's figure it out. And then that'll give you some better sense of how ridiculous my test questions are when I give you things in meters per second that make no physical sense. But the thing is, you guys have no kind of intuition for what meters per second means. So I could put something with 400 meters per second, and it wouldn't dawn on you that, oh, that's ridiculous. If I put it in miles per hour, you'd be like, what? Because you know miles per hour, right? You guys drive, right? Yeah. It's a commuter school, am I right? You're like, we're in the dorms. Fine. Enjoy your mega dorms. Let's see here. Now I don't remember if I multiplied by 50 or not. What'd you guys get? 22.35? 22.35 meters per second. Is that right? Did I do that right? Yeah. Wow. So I think I gave you a problem recently on a test that involved 40 meters per second. How fast was that? So if you multiply this by 2, right? 100 miles per hour is what? 44.6 meters per second. So if I tell you something like, you know, some pitcher throws a baseball at like 50 meters per second, you should be like, what? Like there's been one player in all the history of Major League Baseball who's had that kind of speed, right? There was some guy who could throw it like 110 back in the day, right? No? You guys don't care.